Good morning, students. Welcome to the class on spectroscopy. We were discussing carbon-13 NMR spectroscopy. In carbon-13 NMR spectroscopy, we don't do integration of signals like in proton. We don't do any integration. There are two reasons for this. One is due to the NOE enhancement. Due to the NOE enhancement, we will observe increase in the intensity of the signal that we cannot calculate. And another one, C13 nuclei require longer times for relaxation. So when we irradiate C13 nuclei with RF waves, we will not continuously irradiate them. We will irradiate them in terms of pulses. So pass the radiation for a moment, take a breath, then again pass the radiation. So what we will do, we will excite them, we will give time for relaxation. But C13 nuclei, longer times for relaxation. So before they relax in the previous irradiation, next irradiation will start. So due to that, the integration may not give proper results. So we don't integrate C13 NMR signals. Another important factor is off resonance decoupling. What is off resonance decoupling? Off resonance decoupling gives proton coupled C13 NMR signals, but with a weak intensity, but with weak coupling. When we have proton coupled spectrum, I'll explain it using this example. When we have proton coupled spectrum, what we will observe? We will observe a triplet for this, a triplet for this, a quartet for this signal. So we can easily identify how many protons are there on each carbon. It is a very useful information. But when we do proton decoupled C13, all these will give signals only, singlets only. So because of the decoupling, we don't get useful information like how many protons are present on a particular carbon. So in order to get this information, what we will do half resonance decoupling. What is this half resonance decoupling? In this technique, the frequency of the decoupler, that means second RF wave source, is set either upfield or downfield the normal proton spectrum. So when we want to decoupling, what we will do? We will use a decoupler and we will irradiate with high energy. But in the half resonance, what we will do? We will set the decoupler either upfield or downfield. So it does not exactly matches with the proton energy. So we will set the decoupler either upfield or downfield to the normal proton spectrum, and also we will apply low power. We will apply low power to the decoupler. Due to this, what will happen? It will not eliminate the coupling. It will keep the coupling, but the coupling will be very, very weak. If the coupling is stronger, we observe multiplets which may mix with neighboring signals. But when we have weak coupling, the individual peaks are very clear. So in this case, the two triplets, the triplet another triplet, and a quartet. In the case of strong coupling, these two peaks may combine because of strong coupling we observe a large coupling constant. So these two peaks may come closer together. It may give a confusing data. But in a off resonance decoupling where we will have weak coupling, these two peaks will be well separated so that we don't observe, we don't get any confusion here. Okay. So this is what half resonance decoupling. So because of half resonance decoupling, we get the information for the multiplets. At the same time, the multiplets may not combine with other peaks because we have only weak coupling. Now we will discuss distortionless enhancement by polarization transfer. In DEPT technique, generally we get 4 carbon 13 spectra. We collect 4 carbon 13 spectra. The lower one is generally the C13 NMR, general C13 NMR, where we get signals for all the carbons present in the molecule. And the next level is DEPT 45. Here we will get the signals of all carbons with any number of protons. If a carbon is having hydrogen, it will give a signal in DEPT 45. If it has 3 hydrogens or 2 hydrogens or 1 hydrogen, it will give a signal in DEPT 45. If it doesn't have any protons attached to the carbon, it doesn't give the signal here. Whereas normal C13, it gives the signal for all the carbons present in the molecule. All non-equivalent carbons will give their signal. In DEPT 90, we get carbon signals with single hydrogen. So here all carbons will give their signal. Here only carbons with protons CH3, CH2, CH will give their signal. Here only CH will give signal. So DEPT 90 section, we will get signals resulting from the CH unit. In DEPT 135, we get positive signals for CH and CH3 units. That means if carbon is having odd number of electrons, we get a positive signal, and we get a negative signal, negative peak for CH2 unit. If a carbon is having 2 protons, we will get a negative signal. For example, we will discuss the DEPT for this molecule. This is isopentyl acetate, 1, 2, 3, 4, 5. Isopentyl acetate. In isopentyl acetate, ester will give around 180, largest delta value, then oxygen attached, then this one, and this is the least. Next. So A, B, C, this is D, E, F. Okay. Right. So this is the order of the carbon signals. So we will get a singlet around 172 ppm, Then at 77 we get a triplet from solution solvent. Then at 52 we get a singlet. At 37 we get a singlet, and then 25, 22 and 21, and finally 0. So I'll write the values 25, 20, 25, 22 and 21. So these are the 4 signals. This is from carbonyl, oxygen attached, C, D, E, F. Okay. Now, when we look at the DEPT 45, it will give carbon signals except carbonyl. Why? Except this carbonyl, all other carbons are having hydrogens. So DEPT 45 will give carbon signals which are having hydrogens. So we will get a signal, this 52, 37, 25, 22, 21. So we get all these signals. Okay. Take a correction. This is F, this is E. F means these two methyl groups. This is E, CH. Now in DEPT 90, what we will get? We will get only signal from CH. Where is CH? Only this E. Only this E, 21 peak. Only this 21 peak. In DEPT 135, we get positive signal for CH and CH3. C is a CH3, F is CH3, and E is also CH. So we get positive signals for these. Whereas CH2, these two will get negative peaks. B, C, D, F, E. Here B and D, they will give negative signals. B and D will give negative signals. B and D, because they are CH2 units. They will give negative signals. Whereas this C, F and E, they will give positive signals. C, F and E, they will give positive signals. So from this, what we can say, when we look at this DEPT 135, the negative peaks are from CH2, positive peaks are from CH and CH3. When we look at DEPT 90, we get only CH signals. So compare these two. From this we can clearly say this E is CH, C and F are CH3, B and D are CH2. So this is an useful information to identify the number of protons attached to each and every carbon in the carbon-13 NMR spectroscopy. We irradiate carbons and hydrogens simultaneously with a complex program of pulses. So when we want to have DEPT carbon 13 spectra, we will irradiate both protons and carbons with a complex program of pulses so that it generates 4 different DEPTs. So these are useful for identifying carbons without hydrogens and carbons with CH, CH2, CH3 units. Now we will discuss some model compounds. How many carbon signals can be expected here? How many carbon signals can be expected from C13 NMR? As I said, C13 NMR will give carbon signals which are non-equivalent. So all non-equivalent carbon signals will be observed. Say for example, all these 3 methyl groups, they are present on this carbon. So all these 3 methyl groups are equivalent. So all these 3 methyl groups will give only one signal. So this CH3. So this carbon will give one signal, this carbon will give one signal, this carbon will give one signal, whereas all these 3 methyl groups, they will give only one signal. So altogether we expect 4 signals here. Similarly, I will give some practice problems. You expect how many signals can be observed here. When you expect how many signals that are possible for a compound in C13 or proton NMR, just take some symmetry element, a mirror axis, so that we can easily identify the number of signals that are possible for a compound. For example, take a symmetry axis like this. So these 3 carbons are chemically equivalent with these 3 carbons. So we get only signal for these 3 carbons because these 3 are chemically equivalent. So A, B, C, only 3 signals. So similarly practice these 2 problems. I'll write some more problems here. So take a moment and try to write the number of signals possible for these compounds. For this compound, it is a symmetrical molecule where we can take the symmetry axis like this. So these 2, this will give a signal B, C, D, E, F. Whereas this F and B, they are symmetric, chemically equivalent. E and C, they are also chemically equivalent. So we don't get signal for this. So altogether we get 4 signals, 4 carbon 13 signals here. Yes, similarly here also we can take a symmetry axis like this. A, B, C, D, E, F. B and F are identical. C and E are chemically equivalent. So we don't get signals for E and F. So altogether we will get 4 signals here. Here also we will get 4 signals. For this aromatic compound, toluene, we can draw a symmetry axis like this. Of course, methyl group we will get a signal B, Okay, we will remove this. A, B, C, D, E, F. Since it is a chemically equivalent carbons, B and F are chemically equivalent, C and E are chemically equivalent, we will get 4 signals from the aromatic ring plus 1 signal for the methyl. So altogether we get 5 signals for toluene. We will get 5 signals for toluene. Here we can take a symmetry axis like this. So we get only 3 signals here. We get only 3 signals here. Here we can take a symmetry axis like this. A, B, C, D, E, F. B and F are chemically equivalent. C and E are chemically equivalent. A and D are not chemically equivalent. So A and D will give their signals. Among B and F, we will observe one signal. C and E, we will give one. It will give one signal. So altogether, we will get 4 signals. 4 signals. Remember, when we are taking the axis in between the bonds, we are getting only 3 signals. When we are taking the symmetry axis along the atoms, we are getting the signal for these 2 atoms and chemically equivalent atoms. Here we can take the symmetry element like this. So we can get the 3 signals, 1, 2, 3. Only 3 signals. Please take a correction. Here both A and C are also chemically equivalent. So we get only 2 signals here. A and C are also chemically equivalent. When we take a symmetry axis like this, these 2 are also chemically equivalent. So we get only 2 signals, A and B. The number of signals in the carbon-13 NMR spectrum of are 4-methyl pentanol. So when we want to predict the number of signals, we need to take the structure. This is an important problem. 4-methyl pentane 2-ol. Pentane 4-methyl 2-ol. 1, 2, 3, 4, 5. So this is the structure. Now look at this molecule. This 5th carbon, for example, I write A. These 2 are chemically equivalent, so they will give only one signal, and all others are chemically non-equivalent. So they give different signals. So altogether we will get 5 signals here. We will get 5 signals. Now you quickly recall the intensities of CD3Cl. CD3Cl. How many number of carbon signals do we expect for these 2 compounds? Look at these 2 compounds and give the number of signals. When we look at the first molecule, it is a symmetrical molecule. We can have a symmetry axis like this. Or in a simple manner, you take a symmetry axis like this. Both are mirror images to each other. So they are chemically equivalent. So we can expect signals from 1, 2, 3, 4, 5, 6, 7, 8. There is also another possibility. We don't get 8 signals because these 1 and 5 are chemically equivalent, 2 and 4 are chemically equivalent, 8 and 6 are also chemically equivalent. Because we are getting 3 chemically equivalent, so instead of 8 we will get only 5 signals. But here, see, it is also chemically equivalent when we take the axis like this. So it gives only 8 signals here.